Can you see my screen?
Yes, ma'am.
Okay, thank you. All right, so let's go to assignments. Go to homework 2. Okay, in fact, you may see that here I added that the use of microstrip line equations included in chapter 3 of there, but I would like to go to the homework first. So you're saying homework 3. Okay. So what we wanted to do is to design, now that you have solved this problem, number 2, all right, I would like you to design the matching network, considering a 50 ohm microstrip line printed on Duroid, and assume that frequency. Okay. In chapter, if you go to what I have included in homework 2, this one, and you go to section, that is going to delay it a little bit. So let me do it from my laptop because it takes time for this to upload it. So let me see. I'm going to, 1 second, there, here. All right, so this is the chapter that you have to read, remember, to solve the problem. So in section 3, which is all the microstrip lines, planar transmission lines, go to section 3. Section 2 is mostly what we've done, ideal transmission lines. So section 3.6, if you go and look at, just read it even briefly, you will see in microstrip, there, 3.5 is microstrip, and then 3.6 specifically there, microstrip design formulas. So let me ask you a question. Do you read the material before you start doing the homework? Or you try to do the homework and then you're looking for the material you need?
I usually try to read beforehand, but this has been a busy week, so I really didn't get a big chance to read beforehand. So I was trying to get the homework done and look at the same time.
Yeah, so that is a problem, all right? I mean, sometimes you don't have to read carefully. You can just screen it and see where the material is that you need to have. Because what you need is exactly here, see? And you don't even have to struggle for that. It tells you exactly how to design the line for a characteristic impedance that is above 44 ohms. And that's called high impedance, and a characteristic impedance which is below 44 or something. And then it gives you the formulas, exactly how to do it. What to find W over H practically, right? That's all that you need to find. The width of the line for the transmission line and the width for the line for, I mean, all of them have the same Z-naught, right? So practically that's the only formula you need to use. So my advice, when you try to solve homework, don't solve homework by either reading only the outlines. I mean, it's good to read outlines from my lecture, if you have them, or to read other things, but also scan the material that I'm asking you to read. Because without that, you will not be able to solve the homework. And I know sometimes it's difficult to read the material, but without the material, without reading it, I don't know how you solve things, all right? So that is exactly what you have. 3.6 is the chapter you have to read, and also has an example here. which I like in this section. So do you have any more questions about that? I mean, what was which part of this, maybe I need to go back and ask, was those equations that you did not have, or was something else that also made it difficult?
It was those equations.
Okay, so now you have them. Any other questions before I go to solve a problem? I will practically solve problem 9, similar to problem 9.4. But before, let me see whether it's that done from here. 1 second. I'm trying to go back to assignments. I want to see how many problems I give. Okay, I was going to try to solve problems 4, but any other questions about the other problems? I will not solve problem 4. I will solve something similar. Go ahead.
I had a question, just a real quick one on number 2. When I'm trying to solve, like I was watching the solving session 3, and I noticed that you had needed to solve for Z01 in that specific problem. And for problem 2 of the homework, am I needing to solve like for the impedance of, for example, if I use a shunt?
No, look at that. Read the homework carefully. The problem, it says, assume that Z-sub S is 50 ohms, that Z-sub L is 100 minus J30 ohm, and find the ideal transmission line matching network so maximum power is delivered to the load. Assume that the ideal transmission line sections, all sections in the MN, ideal transmission line sections are both inline sections and in the stub. And I say, assume that the ideal transmission line sections have characteristic impedances of Z0.
Okay, that's what I was confused about. I didn't know if it was just for the stub or if it was just
no,
for the
it was
but
everything.
Okay.
Yeah, because the stub is made out of a transmission line, all right?
Right.
The stub is a transmission line that is terminated, either in a short or in an open. And when I say that assume that the ideal transmission line sections in the matching network have characteristic impedances of 50 ohms, that imply that every single ideal transmission line section that you have is going to have that Z0.
Okay, thank you very much.
Sure. Any other questions about that? About any of these? Okay. How did you find problem 4?
I haven't got to that one yet since we haven't gotten problem 3 done, and it required problem 3. So.
Okay. Anybody else? So I guess it's about the same. So why do I not solve a problem similar to 4? Practically, I'm going to solve another matching network. And then for that other matching network, I will plot the magnitude of the reflection coefficient that shows here as a function of frequency, all right? And then identify the 3 dB frequency points. How about that? Is that okay with you?
Yes, ma'am.
Okay, perfect. Thank you, thank you. All right, so let's try to do that. Okay, let me see, 1 second. So I will do a similar problem, okay, and I will design it. I will just select other impedance. So let me try here to go to okay, I'm trying to find notability. That's not that. Where is notability? There. All right, so that's so. Practically, when I say week 2, I exclude, it's supposed to be week 3. So in any case, I'm going to homework 3, and I will make some homework 2, I'm sorry. And I will then say notes from office hours. Oops, not. Okay. September 10. Okay. So let's assume the following. I will solve a matching network problem, first of all, just for also for practice. So first example, let me say example. Okay, and then, all right, consider a 50 ohm source with V/S equals 2 volts. All right, exciting a transmission line terminated a 50 ohm exciting a 50 ohm transmission line terminated at a load Isabel equals 80 plus J 100 ohms. Okay, so find a matching network that helps transfer the maximum power from the source to the load. Okay, first of all, and then second, to find the 3 dB bandwidth. Now I'm talking to you as if I'm asking you to design something. This is how I would do it in practice, all right? And then I will try to explain what that means, as I did in the homework. So for solution, let me first of all ask you some questions. When I say that the matching network helps transfer maximum power from the source to the load, this maximum power, is it, what number is it? Is it real? Is it complex? Is it imaginary? What do you think? I mean, if I write power, it's going to be in watts, is it going to be a real number in watts, or is it going to be an imaginary number in watts, or is it going to be a complex number in watts? What do you think?
For maximum, I would imagine it'd be a real number in watts.
Exactly. Power is always a real number. Always. Even if it's not maximum. When you say power, it's always real. When there is when you start looking at later, at what people are calling the Poynting vector, you're not gonna see it in this class. That implies a complex number where the real part is the power and the imaginary part is the energy. So power, always real. Energy, always imaginary. Why do I say that? Because power is something that is transmitted from one place to another. And we only transmit real power, all right? But energy is something that stays in one place. And if it's not propagating, it stays there like the energy in a capacitor. It's electric energy. The energy of an inductor is magnetic energy. Those are always imaginary numbers. So keep that in mind. And whenever I say power, remember always real. So here I would say power, always real. And if I send from my source to my load, which is complex, power, which part of the load is going to absorb it? The power. The 80 ohms or the J10 ohms?
I apologize. I did not hear your question. I was taking care of my
Okay.
dog.
No, okay, no problem. The real power, if it goes, I would like also to hear somebody else who is connected. All right. So I would like all of you people who are connected with me to participate in the discussion, one way or another. So the question that I have is, if I send real power from the source to the load, and the load is an impedance that has a real part of 80 ohms and an imaginary part of 10 ohms, which part of the load, the 80 or the J10, is going to absorb the power?
I'd say the
Okay.
I'd say 80 ohms.
Yes. Thank you. Why is that? Because 80 ohms in the load is a resistor, and J10 in a load like this is what? It's an inductor. Whatever you see in the imaginary component of the load is an inductor. If it's positive, it's a capacitor. If it's negative, if the load is a Z impedance. So these are very fundamental concepts, and you will need to pay attention to them. So when you see numbers, you understand physics. That is extremely important. This is not a math class, all right? When we do circuit design, we use math. Math is like a language. Now, I learned English. It's not my first language, but I learned English because I needed to communicate with people. Here, I was born in Greece, so Greek is my initial language, but then I have to speak in English, because if I speak Greek, you don't understand what I'm saying. So math is a language for us, for engineers. This is how we communicate physics. So if I say that I have a load which has a resistor and an inductor, then I write it as 80 plus J10. So when I see 80 plus J10, is not just a complex number. It has a meaning, a physical meaning. Like when I tell you, let's go for lunch, and send you text, all right, and say, let's go for lunch. Lunch is not just a simple word, it has a meaning to it. So when I say lunch, you don't see lunch, you mean that we're gonna go and eat together at 12 noon. That's what it means, all right? So there is meaning to math that we have in circuit design. And I suggest that you try to always ask the question, what does this mean physically? Always ask when you see something, what does it mean physically? That should be your question, all right? Because if you understand that, you're gonna also understand, you're gonna try to avoid a lot of mistakes you would do if you just purely were to treat this as a mathematical problem, all right? So I'm asking you these questions so you understand how you need to think in this class and as engineers practically. All right, so now let me draw what I have. Somebody tells me that I have a source. It's here. The source in the frequency domain obviously gives me 2 volts, which means in the time domain is going to be 2 times cosine omega t. Omega will be the frequency, but we are solving things in the frequency domain. Okay, and then it has an internal impedance, Z sub S. And Z sub S is, it says, consider a 50 ohm source, means that Z sub S is 50 ohms. So practically it means, what does it mean? That the internal impedance of the wall on the voltage source is resistive, 50 ohms, it's a resistor. Then here I have initially a transmission line. The transmission line has a characteristic impedance of 50 ohms. And this transmission line is, I don't tell you how long it is, but this transmission line is terminated at a load. And the load is complex. So the load practically has a resistor and an inductor. And if this resistor is R sub L, and this inductor is L sub L, so then my load, Z sub L, would be R sub L plus J omega L sub L. So obviously, since I give you that omega L here, what do I give you? I give you that this is 80 ohms, a resistor, and then I give you that all of this is 10 ohms. What does that mean? That at my design frequency, at the design frequency, F naught, I have that omega L is 10 ohms. All right. Now, I do not necessarily need to give you at this moment the design frequency. The design frequency, I will need it only if I find everything in terms of a wavelength. I don't need to specify the design frequency. The design frequency will be specified if I need to have physical units into the various quantities, all right? So for example, the only unit that I have not specified physically or electrically is this one, which is the length of this line, and I will assume it is D. If I need to find D in wavelengths, I don't need to specify the design frequency, because obviously I will find D in wavelengths of the design frequency. The moment, however, I'm asking you, or the moment I'm giving you a design frequency, then you can find D in physical units. All right, so you will see what I'm saying. So let's assume in this problem that the design frequency is 1 gigahertz. How about that? Okay, I selected this. All right, now I know what is F. I did not say here. Sorry, that was not equal. Here it meant. All right, since I know that F naught is 1 gigahertz, so practically from here I know that 2 pi F naught L is 10 ohms. Okay, that's what it means. Now, if I have this circuit the way I have it here, I know that, let me call also, put the unit, the ports here, A prime, B, and B prime. From things that we have learned from 322, we find that our load, this one here, is not the same with Z naught, and therefore the reflection coefficient here, if I leave the transmission line the way it is, my reflection coefficient here, gamma, at B prime, what is this gonna be? So I know that at B prime, we have what? That gamma at B prime equals Z sub L minus Z naught over Z sub L plus Z naught. And if I replace it there, what do I find? That Z sub L minus Z naught is gonna be 80 minus 50 plus J 10 over 80 plus 50 plus J10, which makes it 30 plus J10 over 130 plus J10. And that is 3 plus J over 13 plus J. And how do I make that into a magnitude and phase? Practically, I multiply numerator and denominator by the complex conjugate of the denominator. And what does this give me? 3 plus J times 13 minus J. And in the denominator gives me 13 to the second power plus 1. How much is 13? 13 to the second is 169 plus 1 is 170 here. And then I have 3 times 13 plus 1. And then I have plus J 13 minus 3 plus J10. Okay, which gives us 39 plus 140 plus J10 divided by 170. And that gives us that 40 divided by 170 is 0.235. 0.235 plus J and divided by 170, 0.06, 0.05, say 9 approximately. So practically I have a strong reflection at BB prime, which means that if then this reflection comes back, and if my reflection at this point, gamma A prime, is with respect to ZS is very high, I'm not going to have the maximum power to go from 50 ohms to R sub L to L sub L. Practically, to be able, so that implies here, I will say that statement and then I will prove it to you, that implies that I have a mismatch between the source and the load. And I will have this mismatch because gamma BB prime has a magnitude and has a phase. All right. And the magnitude from here, I remind you things that you should have seen before. The magnitude from here is 0.235 square plus 0.059 square. And then it has a phase where the phase, by some gamma, the phase is the inverse tangent of 0.059 divided by 0.235. And what I find from here is gamma sub B prime is equal to, let's find the square root first, is 0.235 second, and then plus 0.259 square equal, it's and then square root, that is about 0.242, and then has a phase. I'll find the inverse tangent of 0.059 divided by 0.235. And if I find the inverse tangent in radians, let me do it in degree radians, in fact, is 0.245 rads. Or if you want to turn rads into degrees, I will say do degrees, 0.059 divided by 0.235 equals, still very small. It's going to be, let me see again, 0.059 divided by 0.235 equal, and then inverse tangent, 14 degrees. So is 0.242 and 14 degrees. Okay, why did I write it like this? Because on a transmission line, the reflection coefficient has the same magnitude everywhere, if you remember from ideal transmission lines. So that tells me that if magnitude of BB prime, and let's assume that this is Z equals 0 and this is Z equals D. If the magnitude of gamma BB prime at Z equals D, which is the load, is 0.242, then the magnitude of gamma BB prime at point Z equals 0 is going to be the same, which means I'm going to have a mismatch at AA prime. And if I have a mismatch at AA prime, then I'm not going to get the maximum power going through. All right, that's what it says. So there is no, what I say from here is the following. there is no length D of the transmission line that I have included which can give us maximum power transfer to the load. Why is that? Why do I say that? What is the condition on gamma? At what point we have a maximum power transfer from a source to the load? The load is here, everything that starts here. What is the condition? The condition is that the input impedance at AA prime has to be the complex conjugate of Z sub S. So the input impedance of 8A prime at AA prime has to be 50 ohms. So for a complex conjugate, the question is why? Because for maximum power transfer to the load, Z at input at AA prime, which is this one, okay, the input impedance at that point. Let me lower this a little bit. So you see that? Z in prime input at in prime, at AA prime, has to be 50 ohms. And if that is 50 ohms, that gamma at AA prime will be Z input at AA prime minus ZS over Z input at AA prime plus ZS. And because both this is 50 ohms and both this is 50 ohms, then practically this gamma AA prime has to be 0. All right, that's the only condition, this one, to have a maximum power transfer from the load, the source to the load. All right, that does not happen because we proved that the impedance that we have at AA prime is different than 50 ohms, or we proved that the reflection coefficient at AA prime is not going to be 0. We proved that the reflection coefficient at AA prime, all right? So let me write it here. At AA prime, the magnitude is equal to the magnitude of the reflection coefficient at any other place on the line, which is going to be 0.242. So as a result, one section of a line is not good enough to bring a to have a maximum power transfer, which means just this section of the line is not enough, which means that we have somewhere to use a stub. Okay, so this one told us that conclusion, to have gamma at AA prime equals 0, we need to use a stub somewhere on the line. And usually we do it either in the beginning, close to the source or close to the load, which means either close to source or close to the load. Okay, and what does that mean? Therefore, that means that we need to find a 50 ohm stub, open or short, specify, and therefore width, we have to specify its length, a length ds for the stub, and then second, we need to identify the length d of the line, that we have already included, of the line. All right. So any questions so far? This is the conclusion. And now we know that we have to add the stub. Any questions before I proceed? Okay. So let me take the original. Copy. Paste. Okay. I will remove a few things. I'll keep this. All right. Then what did we say? This is 80 ohms. J10. Okay. And let me make that smaller. All right. Now we have to place a stub. And because I have a ZL at the end, all right. What I decided to do is to use a series stub for this one. So let us assume that I will use a series stub, and let us assume, where do you want to use the stub, in the beginning or at the end? I'm asking somebody to tell me. Okay, who's gonna tell me? Where would you like to use the stub, in the beginning or at the end? Can you guys hear me?
Yes, ma'am. How about at the end?
Okay, at the end. Let's do that. All right, so we'll use so instead of saying at, I said at the load. Okay. So now I will move this one. Okay, I'll make it a little smaller. Then I will move this one. there. And I will place a stub there. I will do it, say, another color, green. So here, the stub also is going to be 50 ohms. We said every section of the transmission line is going to be 50 ohms. So I make it 50 ohms. All right, the stub at the end has to be open or short. So I don't know what it's yet. I have to change to select it. So for now, I will say it's open or short. And I'll tell you how we select those at the end. So let me call, I had this A prime. Let me now call this C prime, and then here, this B prime, okay? Because you will have multiple ports. All right. Now, what you need to think of in the following way. I have here a an input impedance, Isabel. So Z at BB prime is Isabel. Then I have this input impedance, and this is Z, C prime, B prime, which is the input impedance of the stub. And then what I have is, if I replace these two with impedances, practically what I'm going to have is something like this. Duplicate here. And I will replace this by the two impedances, so you will see them like that. One. So one is here. And, sorry, the other is here. No. And it's green rather, this one. Okay. So B prime, and this is Isabel, and this is Z, C prime, B prime. Okay. Now let's think what we need to do in this case. So I will solve the problem in two different ways, all right, for you. So this is without the Smith chart. So this solution is without Smith chart. And then I'll do one with the Smith chart. All right, and then what we're gonna do is move a little further down. Okay. And then I'm gonna move this a little bit further down. So you know how to do it without a Smith chart or with a Smith chart. Depends on what you feel most comfortable with. Sometimes the Smith chart, or many times, is the easiest, but in any case, let's see. This one is not a difficult one. So I have that. If I want to make the reflection coefficient, if I want to make the input impedance here, as I decided previously, 50 ohms, if I make it 50 ohms, I have perfect match at AA prime. All right, so I will have, it's like because they are not complex, neither ZS or Z in at AA prime. So ZS is going to be the complex conjugate of AA prime. Since they are not complex, they're going to be identical. But I will say it like this, which implies that if I make my Z in at A prime to be 50 ohms, practically, I will then be able to have a perfect match at AA prime, so full transfer of the real power. And because my transmission line has no losses, it's going to go eventually to the load. And because my stub is only reactive, eventually it's going to go to the load. All right? That's what I said. Now, if I try to solve this problem the way it is, and let's assume that you want to solve it without the Smith chart, the only thing you can do by putting there a stub at the end of the line is, so the stub, observations, all right? So the stub is going to give me always an input impedance, which is reactive, all right? Always reactive. So practically it's going to be a JX. And X positive or negative. And if I want to cancel the reactive, so the only thing it can do, so practically here, this input impedance at CC prime, therefore, the input impedance at CC prime is going to be the sum of ZC prime B prime plus ZL. And from here, what do I find? I find that Z in at CC prime will be at best equal the real part of ZL, which is going to be 80. There's nothing else I can do when I put a stub at the end, but change the, like a series stub like that. So, but change the impedance to have a real part of 80. But if the at Z input at CC prime, I have a load of 80 ohms, the reflection coefficient at CC prime is going to be not 0, which means that I will have a reflection at AA prime. But if I do that, if, however, that happens, then my reflection coefficient at B prime is not gonna be 0. Therefore, it's gonna have a magnitude, not 0, which implies that the magnitude of the reflection coefficient at AA prime is not gonna be 0, which implies that the input impedance at A prime is not gonna be 50 ohms. So that cannot help me. This solution is not possible. All right. So at least we know that we cannot use a series stub there at the end. So instead of then trying to do all of this, if you don't want to use the Smith chart, my advice is go to the Smith chart, because the Smith chart is going to give you the correct solution without second guessing. All right. Because this is second guessing here. We guessed that we could solve the problem like this. So without the Smith chart, we cannot solve it. All right. To not give, we do second guessing, as they say, of what the solution can be. And we all come out to be wrong. Let me write it here. Let me see. Second guessing. which implies always wrong, or we will have to try every possible combination. All right, so the best way is to go through the Smith chart. And I will say for 99% of the cases, when you have a matching circuit to develop, go with the Smith chart solution. All right, so that is another thing that you have come to realize through this experience. So now I'm going to copy a Smith chart and see how we're going to solve the problem. And we will solve it quickly, rather, and without too many calculations. All right. So let me find a Smith chart to copy. Not here. Oh, I know where to find here. Okay, I'll use that and I will clean it up, copy. And then all right. Okay. And then I will clean it up here. All right, what do we do to go to Smith chart? Let's bring the original problem, all right? This is our original problem. We'll bring it back so we have it next to us to see it. Okay, let's see what we're gonna remove. Okay, remove this. And that is 80. We'll put this one here. $80 plus J10. All right, so we'll remove this. So we know from matching at AA prime for maximum power, we know that Z in at AA prime has to become 50 ohms. So we have to add a stub somewhere. So this becomes a 50 ohms. So what we know here, let me write it explicitly. So we know that we have to add a stub so that Z input at AA prime is 50 ohms. Okay, so that is number one. Number two, what we do, to use the Smith chart, we normalize all impedances with respect to 50 ohms. So normalize with respect to 50 ohms. Okay. So what happens? We don't have much, we have ZL practically. So ZL here. So normalized ZL becomes 1.6 plus J 0.2. Okay. So now we have to find ZL, which is the load to this line, all right, the normalized load. So we have to find the circle that shows the real part, 1.6, and 1.6 here is there. So we'll write the circle of the resistance, normalized 1.6 here. And then the imaginary part is 0.2. 0.2 is, I'll do it with green. It's on the positive higher upper part of the Smith chart. Not this one, excuse me. That is not working like this. Okay, 0.2. And so forth. The intersection between the two is this one. And this is normalized load. So this is gonna be ZL normalized. Okay, now from ZL, what we can do? We can do two things. ZL can only move somewhere. I mean, we can move along the transmission line to find where we are going to place the load, because we know that at the end we cannot place the load. To move along the transmission line on the Smith chart, you have to find the circle here that has its center at the center of the Smith chart, and it goes through the load. Okay, so let's see. Okay, so this is the purple one. Is the, in fact, if I could also make it like this. The purple is the circle that shows our movement along the transmission line. This purple circle shows us moving along the transmission line from the load towards the source. To move from the load towards the source, we're moving in this way. So since ZL is the load, we have to move clockwise, and then we have to decide where we are going to stop. So the question is, where am I going to stop if I move clockwise? So let's assume that I have to stop. I will have to stop somewhere where I will be able to place, I will have them to move and stop somewhere where I will be able to place a series stub. I'm using with impedances, all right? I'm working with impedances rather. So let me, in fact, show you how I'm gonna take this, make it, well, I will make it a little smaller here, and I will make it a little smaller there, and I will move this one to the left, and I will move, what am I gonna do? I will move this one to the right, there. And let's assume that this our initial line is, I just made it longer. and here. And let's assume that I want to move in, let me erase this because we can select ourselves D. And I want to move here from the load. I want to move here from the load until I find a place where I can place a series stub. And if I not find this place, then I can place the series stub here. All right, so in fact, and here, and you will see how I'm gonna do this. I will place a stub that looks like this. And I have to decide whether it's open or short. Open or short, I will put a question mark. All right, and then I have to find how much is this distance. I have to go to place the stub and how long the stub is going to be. So practically now I have to find this distance, D1. I have to find this distance, let's call it D sub S. And then I will have to select this distance, D2, all right? Because now what I decided to do is I said, okay, I cannot put the stub at the end. Obviously, if I can put it somewhere in the middle of the line, that will be very helpful. So, okay, that's how I'm gonna place it. And I've been told that everywhere I have to use a Z0 equals 50 ohms. All right, so now I will move on this purple circle and I will move until I find, let me use another one, until I find this circle. And why am I gonna do that? I wanna do two things as I move. Here, I want to go away from this, obviously, but I'm moving along the transmission line towards the source. And then if I wanna put a stub, the stub is gonna be reactive. So at the point where I place the stub, my resistive part is not gonna change as I'm placing the stub, only the reactive, which means that when I place the stub, if this is point, let me see, if this is point B, and let me call this point C and C prime, and I'm coming to point here C, all right? Then by placing the stub, my point C prime is gonna be here, which means that I can go then and only change the reactive part of the impedance. All of these show impedances, all right, if you remember. So this one practically here, when I have B, that implies is my load. You see it here. When I have C, this, let me do it also. Well, excuse me. This point C is gonna be the impedance as I see here. And this impedance is gonna be the impedance towards the load at C point, all right? So at C. Then I put the stub, and the stub is gonna present this impedance, which is gonna be ZCC prime. And therefore, when I add the stub, the total impedance that I will see between these 2 points, let me call, in fact, this point E, and E prime. And I can call this, in fact, Z E prime C. All right. Then the Z input at E C prime is going to be Z C C prime plus Z E prime C. All right. And this is going to be at the center of the Smith chart, which means that this is going to be 1. So when I move from B to C and from C to C prime, practically I've made my, and I can call this C prime, just so we don't, let me do that. So you understand what I'm doing. All right. So practically this is the stub. And this is the input impedance after I travel from B to C. So when I move from B to C, when I move from BB prime here, and then I add the stub, practically I find myself at the center of the Smith chart, which means, let me write now what I was supposed to write, that Z here, Z input at C, let me see, Z input at E prime C equals what we read from point C, which is going to be the real normalized. The real part is going to be 1, and the imaginary part from here is going to be minus J 0.5. And then at C prime, which is the Z input at C, at C prime, all right, the Z input and C prime, normalized is 1. So what that tells me, I have to move on the transmission line from B to C. So I have to make this distance D1. And then I have to add the stub. And then I will have a perfect match right here. And then I will have a perfect match everywhere else. And of course here. And therefore, if I have a perfect match here, have 50 ohms input impedance, that implies that all of the power goes into the transmission line. Okay, so practically, now I have to find, I found how much my impedance here is there, how much my impedance Z input CC prime is, all right, excuse me, Z input at the E prime C prime is this one here. Which is the sum of the stub plus the impedance I see from the section of the line D1 in front of the load. Okay, so what I have now to do is to find the distance in wavelengths from B to C. All right, to find the distance from B to C. So see what I'm doing. To find the distance, I'm connecting C prime to this. And then I'm finding how much this number is here. And this number, I will write it along this line, shows 0.229 lambda. And I measure it out here. All right. And then I'm writing another line. Oops. There. And I'm also measuring this here. And what I read is point, let me write it, 0.3526 lambda. All right, so I started at 0.229 lambda and I ended at 0.356 lambda. So the difference between these two is going to give me D1. So D1 here is going to be 0.356 minus 0.229 lambda, which is 721 lambda. So I have to move along the line by 0.127 lambda to go to, so I move on along this line by D1, which is 0.127 lambda, until I place the stub. And then after I place the stub, I'm at the center of the Smith chart. So no matter how much more line I have, D2 can be any length, because I already have matched it at EC prime. So any length of the line, any D2 is going to give me the same match, because if your reflection coefficient is 0 at any point on the line, it's going to be 0 at any other point. So if I have a perfect match at EC prime, which is here, if I have a perfect match here, then I will have a perfect match here. Okay. So the other thing now I have to do is to find out how long is, so D2 can be anything, any length. D2, any length that you wish to have on the basis of your other design constraints, depending on the space you have available. Okay. And then the only other thing I have to do is to find the length ds of the stub. Okay. Let's now make a decision of what kind of stub I want to use and see whether that makes sense. The best thing to do is the least in size, the least possible in size stub. Okay, we don't want it to be too long, because stubs that are too long radiate like antennas in microstrip. So you try to be in the shortest possible and realizable, obviously. Okay. So let's see. Let's assume, first of all, assume that we want our stub. Assume that the stub is open. Why do I start with this? In a microstrip, what we are doing is going to look like that. So let's assume I had my load here, all right? The load was here in our problem. And then here comes and connects with the microstrip. Okay, that was the initial problem. And then this one connects with the source. Now the microstrip is printed on a substrate. Okay, and let's assume that this is the substrate, the ground. And in fact, let me do this here, that this is the substrate lines, all right? Let's assume that. And let's assume that this is the ground line. So I will make them like this. Let's assume that this is the strip, the thickness of the microstrip. Okay, something like that. And then I will assume that these lines, this substrate goes like this. something like that. All right, and then let's assume that this is my substrate here. So that's how the initial problem looks like. If I were gonna make a stub, if you see the strip lines, I will make it on the top, all right, on this microstrip. So for example, if I'm gonna make a stub, I will have to go by a distance D1 on the line, D1, as I found. Then cut the microstrip there. So cut it, let me see. And then create a, and then on that, create a stub. Right, and then here, what I can do. Okay, can make a stub. That's how practically you do. That's what you do in this geometry. All right. Now, the stub is going to have the ground underneath it, but it's going to be open because the ground underneath it is separated from the stub. This is your stub. This is your stub. The ground underneath it is separated from your stub by the substrate. So practically, you prefer to have an open stub, because if the stub has to be shorted, I will need to open a hole in the substrate. Okay, I want to open a hole like this, hole, and then have that connect with the substrate, and then have to metallize it. And that, in terms of fabrication, is a problem. The hole connecting the stub to the substrate is going to make it, to the metallization, to the ground, is going to make it shorted. All right, so that is shorted, but I would like to make it open. So practically, I would like to remove that, and to remove this, and practically then keep it open. So let's assume that we have a stub like this, and this one here is the length of the stub is this abyss. All right, I called it this up to, all right, sorry, this up to. And I found, excuse me. No, we have not found the length yet. So we found D1. Let's call the length of the stub this abyss. So open. Now, if the stub is open, let's go back to this. Or you can use, well, like we have to go, this one, it goes better. So if the stub is open, what is the load at the end of the stub? If I go here at the end of the stub, what the load is going to be that I see? The stub is open there. So what kind of impedance do I see? What kind of impedance do I see there? Open or short? Anybody? Is there anybody out there? As the
I'm here,
song
ma'am,
said.
but I'm unsure.
It's gonna be infinite. All right, so if it's open, open shows infinite impedance. And open is right here. All right, open. To be able then to find the length of the stub has a, the stub, to be able to go from You remember what we said? We needed to go from z at E prime C to z and input of C prime to be 1 normalized. And from these two, we conclude that z of the stub is equal practically to j.5, because since the stub is in series with this impedance here, and this impedance at that point is 1 minus j.5. That means if I add to this a stub, which is j.5 normalized, then practically the sum of the two will be 1, which is what I want to get. All right, so practically I have that z input at C prime equals to z input at E prime C plus z input of the stubs, and that has to be 1. So from 1 and 2, we conclude 3. Okay, so now we go back to the Smith chart, and I can have a new one, as a matter of fact, if you are interested. So I can copy, if you think this is a little confusing, and get a paste. And I can make it a little smaller. Okay, and then I can clean it up. The only thing I need to remember is the reactance of the stub. So I will erase all of this. Now I'm working on the stub. I have a stub. So for the stub here, oops. Okay, I'm trying to make it as big as I can. I have a stub that has a ZS, the impedance of the stub. So as I see here, all right, this one is my Z sub S for the stub, and this is J.5, as I found above. So what I have to do is, first of all, start at the end of the stub, which is open. The stub is open circuited, so this load there is open circuit. So I'm starting from here, which is infinite. And then I have to go from there towards the, I have to go from the short circuit this direction, and I will have to find J.5, which is J.5 is somewhere here. J.5. Okay, which means that I will have to travel along this direction until I go and meet this one, that point. And that is going to give me the length, all right, of the stub. Okay, now let's see how long the stub is going to be. And here I go from 0.25 lambda. I start there. I pass through 0.5 lambda. And then I continue until I find 0.07 lambda. So practically, ds will be 0.25 plus 0.07 lambda, which is going to be 0.32 lambda. So that tells me that if I use a series stub and open circuit it, which is this long, then I can have a match as I did before, come to the center of the Smith chart, and then from there, any other length D2 is going to give me 50 ohms. That's how you solve this problem, all right? Now, this problem, I have to ask you guys, have you seen problems like this before in 322?
No, ma'am.
Really, no.
Who was teaching 322?
I had Professor Neville. We spent about 2 days on Smith charts at the most.
I also had Professor Nuggets.
Okay, so you will need to practice quite a bit on this because all of the low noise amplifier design will be more complex than this. And this is very simple. You will see the low noise amplifier designs are one step up. So we will need to be able to do and empower amplifiers or even local oscillators that we will need for the receivers. We will need to know Smith charts well. So my advice will be to solve as many problems as you can on the Smith chart. I mean, make up problems like this. You don't need me to give you a problem. You can go and take this problem and try to solve it, follow that, and then you can show me the solutions, you know, put other numbers there, or instead of a series stub, try to put a shunt stub, because a low noise amplifier, to be able to design it, we need to do two matching networks, one in the front of the transistor and one at the end of the transistor. And there is no way you can do these two matching networks without knowing Smith charts. And we're going to use Smith charts also to find the point of low noise, stability, and all of this. That's why these are extremely important. And I'm very disappointed that it was not covered more than this. So what else did you cover in the class? Plane waves or something? What else did you do in 322? Did you guys go to plane waves or wave guides? What did you do?
I'm trying to remember, ma'am. It's been a year since we took that class.
Yeah. My advice is that you try to do, I will try to solve problems like this in all of these problem solving sessions, but my advice will be practice with them and ask other students. It's okay, you know, to ask other students. I have no problem with that. All right. Whenever you get, or ask me, whenever you get stuck, let me know. And I will try to help you, but you will need to practice. And then it's not really very difficult. The moment you do a couple of those, you will see that you will do many more. It's not like the changes, it's the same kind of story. You put your load, you move along the purple circle, you know where to stop. I mean, this is always the same. It never changes to something more complex. It seems complex, but when you start practicing, doing a few problems, I suggest that you do them early in the semester because you don't have as much work. If you don't do them early, these extra problems, that I think later you're going to find it more difficult to catch up. It's going to be really difficult. And then you're going to have so much more work from other classes. So now take the opportunity to practice on these problems. In any case, what I wanted to do next, if you have more time to stay, I wanted to show you how you're going to do the frequency thing. All right, that you have to plot it versus frequency. That's the fourth problem. So now what we know, we are here. You see that I'll take this. If you solve this problem, then I will take this. The other one becomes simpler. So I will take this initial. Oops. copy. And then I will go down here after that, paste. And I will now review what I found. Okay, just a simple review. I found that my load, okay, let me see. What was the load that I gave you in the homework? Let me see. The homework said, homework 2. I don't want to make it more difficult than. Okay, ZLBB prime. Okay, it's 100 plus J. Oh, okay, so here it is. Okay, let's go now and do this problem. The last one was an extra, right? Forget about this. But I wanted to show you, these are the problems we will have to solve for, that's a leftover. I do not want to do anything with this. I will have to remove it. But if you see a transistor, you will have to match this to a transistor and then will give you, like the S parameters will give you reflection coefficient, and then we'll have to find these two. Now I will tell you sometimes how to do this, all right, in this problem. It's a basic problem, but some other times I will not tell you how to do this. You will have to figure it out yourselves. But in any case, so let's try to solve problem 4. Now I know what I've done. I will continue on my solution here because very similar. So now I will clean it up and I will see what I have. I know, let's assume that I make D1 0. All right, you remember what I said, that no matter what D2, D2, no matter what D2 I have, the moment that at this point here, the moment that at this point here, all right, or like here, like this, at this point there, on that, the reflection coefficient has already become 0 because I matched it totally. That means that any length of line D2 will bring my front, my AA prime, to also 0 reflection coefficient. So practically I can say I can make my D2 to be 0. All right, I don't need to have an extra length of line after the stub. So I can make D2 go to 0. If I make D2 go to 0, then here is what I have. I have my initial voltage source, and then I have 50 ohms here. All right. There. And then I will have this. I said I will remove the D2, okay? So let me remove that. So that now is gone. I don't have a D2. Then I go directly to the stub. Which I decided for this, I will make it open. Okay. And then open. I found DS, and I found that to be 0.32 lambda. And then I have the rest of the line, which is D1. And how much I found D1? 0.127 lambda. And then I have my load, resistance and inductance. This is 80 and J omega for the design frequency. L is J10. Okay. Now, I want to find here, what did I say in the paper, okay, gamma. All right, see what I said, what I'm asking you then to do in this problem that I have is if I call this A prime, and I call this B prime, and I call this C prime, all right? What I want you to do is to plot this reflection coefficient where gamma at A prime is nothing else but Z input at A prime minus Z naught divided by Z input at A prime plus Z naught. All right. And I want to find this as a function of the frequency. So how much is the input at A prime? This is going to be the stub as we saw before. All right. The stub plus the length. This is the stub ZS plus this, which is Z input at BB prime. And what did we find? We have found that Z stub plus Z input at BB prime. Okay, so now we're gonna have to be able to do how it changes with frequency. There are two ways to do it, but I will do it with transmission line equations because it's gonna be the simplest. When you go to ADS, you're gonna be able to do it there. So how much is Z input at BB prime? I have a section of a line which is D1 with a characteristic impedance D naught. And therefore, this one is going to be Z naught. And then I have ZL plus J Z naught tangent of beta D1 over Z naught plus J ZL tangent of beta D1. And ZL is nothing else but 80 plus J, I keep the frequency explicitly, omega L, where now omega or L is gonna be 10 over omega naught from here. All right, and omega naught is the center frequency. Omega naught is gonna be the design frequency or the center frequency. Omega naught is gonna be 2 pi F naught. And omega is going to be 2 pi F, all right? And beta is going to be 2 pi over lambda, okay? So then, what do we have? We have found that Z input is going to be Z naught, which is 50 ohms, ZL, which is going to be 80 plus J, and then you have F over F naught, that's where the frequency comes into play, times 10, plus J 50 tangent of 2 pi D1 over lambda. And then you have 50 ohms, Z naught is 50, plus J, ZL, which is 80, plus J F over F naught 10, tangent of 2 pi D1 over lambda. So you put it there, you have the frequency. How much is the frequency compared to lambda? How much is lambda F? Do you know how much the frequency times the wavelength?
See
How much?
the speed of light?
I did not hear it again.
The speed of light.
Yes, yes. Thank you. I'm sorry, I could not hear you very clearly. Absolutely, yes. So now, let's assume this is an ideal transmission line. So it's gonna be 3×10⁸ meters per second. Okay? So, and now you have everything in frequency. That is the Z input at BB prime. BB prime. How much now is this a base? This a base is the input impedance of an open-ended stub, and based on what I gave you in this class, this is going to be ZS cotangent beta DS. All right, where so is minus J, excuse me, it's G naught. Z naught. This is minus J Z naught, which is 50 ohms, cotangent 2 pi ds over lambda. Yes. And then what do you have? That Z input, which now I have made it 50 ohms at BB prime, at AA prime, excuse me, AA prime. Is going to be ZS, which is minus J Z naught. It's 50 ohms, right? Cotangent 2 pi ds over lambda plus this one. Copy, paste, plus this one. Okay. And if you're going to find the deflection coefficient, gamma is Z in at A prime minus Z naught over Z in plus Z naught, which at the center of the frequency is 0. However, when you start, so which is 0 when F equals F naught. But when F becomes different than F naught, then practically that changes. All right. And what I wanted to do in the problem is to plot that. So go to the computer and plot it. And then find the points, as I said here. So I want you to then look at the magnitude, obviously, of the reflection coefficient, and then look at the points, the two frequency points, one at the higher than the design, one lower, because you're going to find, for example, I cannot write on this one, but what you're going to find is that if you plot the magnitude of this, you're going to find that it looks like that. Okay, where magnitude, where this is going to be 0, excuse me, sorry, the other way around. Where this is going to be 0, and this is going to be whatever other numbers, all right? And I wanted you to find, let me see, how did I define that? Oops. Come on. What happened? Okay, let me go to the homework. No. Homework 2, what happened? Why did I not? Oh, there. Okay. Okay, so where is okay, so practically what I want you to find on the computer rather is this is the max, this is 0 gamma max, and then I want to find the points where that becomes half of the maximum value. I mean, it's, you could be anything else, all right? So these 2 points. And then we say that the reflection coefficient is smaller than that, and that you can define it as somewhere of the bandwidth. But practically, the reflection coefficient is going to go between a higher value and a lower value, all right? Between 0, the reflection, the maximum value of the reflection coefficient is going to look like this. So what this is going to be the design frequency. So I want you to find these 2 points. But if you go to the computer and plot it, it's going to look like that here somewhere around that frequency. So I want you to find these 2. However, I would do this on the computer. It's just you have to plug it in and change the value of the frequency from the design frequency. You can choose a design frequency yourself. And I think I gave you already one, which is the design frequency for that was 2 gigahertz. So you go around 2 gigahertz and you see what is the maximum value of the reflection coefficient. And from the maximum value you will plot it across from, like, say, 1 gigahertz to 3, for example. You can plot it. Or you can plot it half a gigahertz to like 3.5, for example. And then you can see how it looks, get the maximum value. You find around 2 gigahertz where the 2 frequencies, one below 2 gigahertz, one above gigahertz, that gets half of this maximum value. So this is as an example. Okay, so did you see how to solve it?
I have a question.
Yes.
What software should we use to plot it? Like ADS? Is that
No, anything. You can put
anything?
it on. Yeah, you can put it on your own calculator if you have, or you can put it. I have not asked you to do ADS yet.
Okay.
All right. So if you happen to know it, it's fine with me. If you don't know it, just go on the computer. Do you know how to write a program? Do you know how to program?
I have an idea, I think.
Have you guys ever done programming?
Yes.
Okay. So if you have done some programming, go there and plot it. Also, you will find, I guess, on the web, some applications where you can plot a function. But I would write a small program, to plot it. It's going to be easier.
Okay.
What kind of language did you use for computing? When you did some fundamental computing, what did you use?
I imagine for something like this, I'd use like MATLAB or.
Yeah, MATLAB is perfect for that.
Okay.
Yeah, probably is one of the easier because it has all of these functions. And in fact, if you want, you can put if you know how to put the microstrip on MATLAB, with this load and these dimensions, it's going to get it to you over a frequency range.
Okay.
Yeah. So any means you find available for this one. But then when we start with ADS, I'm going to ask you to do all of these things in ADS. So I think this is still now practice, on Smith charts. These are still practicing exercises. Any more questions? I will upload this to the, and I will try also to upload the video tomorrow, but I will upload my notes right now.
I have a question
Mhm.
about the quiz that's due tonight.
Yes.
I had a problem with the first question on the quiz.
Oh, I fixed it. You know what
Okay.
happened? Yeah, what happened is on Canvas, you need two different controls, to be able to move your accurate answer. And I think I moved it, but then I did not save it. So I saved it, but now if you have answered, the correct answer is going to give you the right, it's going to correct what it gave you as a score.
Okay. Is there any chance we could have a second attempt for this quiz or no?
No, I think I have, why, what happened? the-
Just to make sure, like, I guess I got it wrong in general for the first one, but it was like worded weirdly for me and I was kind of confused.
Did you submit it?
Yes, ma'am.
I don't know whether you can access it again if you have submitted it already.
Oh, okay.
But
Okay,
you
that's
can-
fine.
Yeah, you can have multiple before you submit it.
Oh, okay.
Yeah, so before you submit it, you can go back and forth in your answers. But the moment
Okay.
you have submitted it, then you cannot do it again.
Okay.
There will be many more quizzes, so don't
Mhm.
worry about that. Yeah,
Okay. Thank you.
sure.
Hello, Professor.
Yes.
I was working also on problem 2 again. The way that I guess that we're given the components are similar to the one that you did at the end of solving session 2, where we have a
Which-
real, I guess,
Can I ask which two are you talking about?
sorry, problem 2 on the homework is what I'm working on, and I said it was similar
Okay.
to the problem solving session
This
2
one.
question. Yes.
Yes.
Because I'm trying to follow like your notes on like just like applying them to the problem so I can figure out the answer. And from the way that at least it's presented, at least to me, I don't know if it's happened with anybody else, but to me the problem seems to be formatted in the same way as the problem at the end of your second problem solving session, where you said that the answer to that problem was that you can't find any components for this circuit.
one. No, number 2 here you can. That was a different one.
Okay.
In this one you find a solution.
Okay. So
In this one you find a solution because I don't constrain you as much. Is that the one I have in front of me?
right, yes.
Yeah. In the other one, you cannot find a solution because I gave you too many constraints. I specified lengths, remember?
Right.
In this one, I don't specify the matching network. So there is a solution to this one, the way I
So-
explained it.
Okay, so for example, like the lengths, like changing the length between, for example, lambda over 4 and 3 lambda over 4, just for as an example, will be significantly different to where you can like probably find an answer between one of the two, for example.
If I don't fix, so in this particular one, if you go to the solution that I gave you, if you see, it's similar to what I have given you, but I did not fix D1, see? I did not tell you what kind of lengths to use. I only told you to use Z0 characteristic impedance everywhere, but I have both D1 and DS. I left them undefined for you to define them.
Okay.
So you can always find a solution to this problem. Always.
Okay. Thank you.
Sure. Just follow what I did here for 2.
Okay, I will. Thank you.
All right. Any other questions?
Yeah, I have one about problem 3.
Mm-hmm.
For that one, a lot of the equations when you try to find the effective permittivity require like to know what W is.
Yeah, they are in the section 6.3 of the notes that I told you to read chapter 3.
Yeah,
3.6.
yeah.
Yes, you found them? You found that?
Yes, that's what I've
Okay.
been looking at.
Yes, yes, absolutely.
But there's isn't there so you just basically choose whichever one you want because it's a design problem, it's very open.
No, the moment you know your Z naught and the moment you know the other, I gave you epsilon, I gave you H, and I gave you the design frequency, and I gave you 50 ohms. So you should be able to find W and W specifically.
Okay.
So the only thing you need to find is the width of the microstrip lines because the lengths you found them from the design.
Yes.
Yeah, so
Yeah.
only the width and the width with the epsilon sub-bar and H that I gave you and 2 is very specific. You will find it from those expressions.
Okay.
In fact, the expressions, let me see whether I can find them here. Okay, let me do them separately. Yeah. Okay. If you go in this one in 3,
Mm-hmm.
3, not in 2, in chapter 3,
It's like page 41 and
somewhere
40.
there, 3, because 2 is just ideal transmission line. So you go here and says design of microstrip 3.6. There they give you tables also, but 3.6 has the exact formulas. Yeah, see?
Mm-hmm.
So here, if you know epsilon sub-bar and H, you find W. And then says for characteristic impedance above 44, which is 50 ohms for us, you use this formula.
Okay. I don't know. The way I did my problem, I don't know if it's right or not, but one of the strips has a different, the Z naught is like 70 ohms
Why?
because you're matching it because you have to go from the 50 to the characteristic impedance is 50, but because you go to the 100 ohms and the 50 ohms, if I understood that correct, is the ZS. So the way, at least the way I solved it, it turned out that for the one transmission line section, it's 70 ohms. So I have a Z naught 1 and a Z naught 2 because I have a stub.
I got that. I mean, you can do whatever you want in a design, all right?
Mhm.
But I want to make sure that you have done it correctly.
Yeah, yeah.
Otherwise, yes, you can choose whatever you want in a design. I mean, that's the nice thing about the design. The design is there are open-end problems, all right? Two of you can have 2 different designs and they can
Mhm.
both be good. A lot of times, the best designs are the ones that meet all of the requirements, which now we don't have all of the requirements. Could be you don't even know how much space you have available, all right, to put this on. You don't know how big your wafer is and all of this. I mean, these are other considerations, but you can choose whatever. I just want to make sure in this problem, are you not talking about this one?
Yes, that's what
Yeah.
I'm talking about.
I just want to make sure that you have the correct, you have done it correctly, and you could have a different impedance. If you have a different impedance in the stop, then you use this formula for a different Z naught. The formula that I showed you.
Mm-hmm.
at 3.6 at the chapter 3.
Yes.
Yeah. So that's, yeah, you can do that.
Okay. All right. Thank you.
Okay, sure. Any other questions? Anybody else? Because if you don't have any other questions, then I will log off. Okay, I'll talk to you later.
Thank you.
Bye. Bye.
Thank you.
Bye.